So welcome back again for the second session on materials this morning. We have two extended presentations, I would say, ahead. One on the work done by DLR in Cologne together with Saarland University, and then a combined presentation on a couple of projects in our program, and both related to the electromagnetic levitator. So we'll start with Dr. Young to talk about bulk metallic glasses.
Yeah. Okay, sorry for the layout. I need to change it later on. But yeah, I'm going to speak on two projects. They are related. They are mainly on bulk metallic glasses. The first one is concerning this new sulfur-containing alloys, where we're interested in both cases, actually, the structure and dynamics of the melt. And in this case, this is a collaboration with Saarbrücken and also in University of Münster. And what I'm going to say is these are still the experiment upcoming in batch 4 and batch 5 of the ISS EML project. So I'm not going to present the result on a space station, but I show you just a scientific case and also what have been done so far on ground and from parabolic flights. On this particular project, we are looking at the sulfur-containing metallic glass-forming alloys. What is new or quite recent is that basically our colleagues at Saarbrücken has discovered sulfur as a new ingredient. Let's say. Actually, it's not new for example, other alloys, but for glass-forming alloys, this is new. And what is interesting is this can be applied to different alloy system at a different sulfur level. That's why it's interesting that we are looking at why this is working quite universal. And the idea behind is also, on the one hand, basically metallic glasses for those of you who are not working there very often. Basically, they have quite special properties. On the one hand, the mechanical property are, especially the strengths are quite good. On the other hand, some of them or many of them are brittle. But with sulfur, they achieve first that a metallic glasses which can work with a high titanium content means that they are lightweight and also has biocompatibilities. And on the other hand, which I will show most of the results on nickel-niobium-based alloy, they are already a quite good glass former. And with sulfur, and recently also they work with phosphor alloys that they are both have high strength and also ductility. So just to show you that there are some here in the engineer strengths, but in both cases, and if you work with a little bit more alloy optimization, they can be casted by both die casting and some of plastic forming, which is a special property of metallic glasses, that you can basically extrude or press them like a polymer, basically, which you can then cast special component. This just is to show you that how the alloy development has been done. So basically the glass forming ability, or in this case, so basically how good or how easy they can form a glass or avoid crystallization. So what we are especially interested in is that when you have a melt, you quench it, that it does not crystallizes, depends on composition. And this is just to show you that this has been matched. So if you start from a simple alloys, so ternary systems, in our case, this is usually low, and how this can be developed into more complicated system. But we, as for carrying out physics studies, we are interested especially in these ternary alloys as a model system, because they are more easy to understand. This is how they did at the nickel-niobium sulfur system. So basically, first look at the different sulfur concentration, and once you find a good concentration range, we moved to basically to optimize the nickel-niobium sulfur ratio, and then we end up with basically these two candidates, which has best glass forming ability. In this case, especially for the experiment on the space station, we are interested in basically the sulfur effect, impact on the structure and dynamic of the liquid. This is not part of the space composition which we did at the space, or we want to do at the space station, but this is an intermediate sulfur concentration alloys where we study the liquid behavior, or especially the dynamics of the liquid as a function of sulfur content. This is partially done also here in the electromagnetic levitator, which you have the same version or similar version on a space station. I will show you also later on, because we have a parabolic fly facility, how this is done. But Florian will talk about more on the facility on the space station. What you see here is, what is interesting is basically the viscosity increases with increasing sulfur content up to something like we studied up to actually slightly higher, but up to the best glass former in this case. And similarly, if you look at the transport coefficient, they are similar trends. So basically, the melt dynamics increased, slowed down with sulfur addition. Which is interesting is usually you will imagine that if metallic liquid gets more viscous or the dynamics gets slower, that they are more densely packed. But this is not the case in this sulfur-containing alloys. We measure the density and translate that in basically the atomic number density in the melt. And what you see is actually they are slightly decreasing, so means that your melt gets actually slightly loosely packed if you want. This shows you again that the sulfur has a special effect. It's not like a standard or conventional alloying element. So structurally there must be something going on. And basically this can be somehow understood that why the glass forming ability gets better, because if you have a slower transport, and if you quench it, it's more difficult to crystallize. But we studied, in this case, also the solidification behavior, and if you want to look at details, there's actually a bit more than just a slower dynamics in this case. Now I move to basically the sample which we intend to investigate on the space station. However, the situation is slightly different in this case. So we measured the viscosity of the melt in both regions. So we measured the high temperature region. Some part of them has been also done on a parabolic flight facility. That's why there are only a few points here. I will show more zooming in the high temperature region later on. And because it's a glass, you can also study, if you're heating it from the glass transition, you can study also the viscosity at the low temperature. In both cases, what you can see here is that basically the viscosity is not changing much. This is the same if you look at the transport coefficient in this case. So between the binary and sulfur containing alloy, they have very similar transport coefficient, except that if one go down to the glass, so below the glass transition, then one sees some differences in the glassy state, that the sulfur alloy seems to have a slower dynamics. This can be understood if you say that the alloying level is very low. So we are only adding 3% of sulfur, so that is not much change also in the alloy composition. But I would like to remind you that also that the glass forming ability is increasing a lot. So just to give an idea, so basically from 2 millimeter, which you cast for a fully amorphous sample, to 3.5, so it's increasing 50%. We look at also at the structure. So this is also a very small change, but here we do see that there are structure changing more. So what you can see is this is in the melt, and what you can see is actually this part of the first sharp diffraction peak is decreased in amplitude. If one look at it carefully, also the position change a bit. So there are structure changes in this melt upon sulfur addition. We look at also in the glass in a different way. So look at basically the medium range order of the alloy using electron microscopy. What one see here is that basically also similar to here, the amplitude, so the ordering of the alloy is decreasing, but here at a different length scale. So basically, it seems like that the sulfur continuum alloy exhibit more disorder, but we are not sure whether this is so the overall concentration of the ordering is changing, or you have more really correlated chains or clusters with what you want. So this is the structure aspect that we have found out. And now I come to the part, basically what we have already done on the parabolic fly campaign. So it's a campaign relatively recent. So we have 2 experiments on 2020 and 2021. When we worked on 2 slightly different composition, because this is actually during that time we are still doing alloy development. What we find out is actually we learned a lot from this parabolic campaign. One thing, so a more technical thing, is if you look at this melting process, you find that at the beginning that one still have a lot of solid, if you want, at the sample surface. This is later on to figure out that this is due to the sulfur layer at the surface. Due to that, we need to go at the beginning at a relatively high temperature in order to dissolve them completely. That's why we cannot measure actually at high temperature, because due to the heating, the sample is deforming a lot. And we can only do good measurement actually when to supercool the sample once and cooling back to relatively low temperature, that the sample is quiescent. That's why the temperature range are rather limited. For those of you who are not very familiar with this kind of measurement, so basically we are doing a oscillating excitation of the sample. And what you are looking here is basically the damping of the sample once you switch off the oscillation. And if this experiment is clean, you see this kind of curve. So what you want is the sample is damped solely due to its internal friction and not oscillating in a strange shape. And from there, you can then derive proper viscosity data. That's why also the reason that the range we can assess in the parabolic flight is limited, because we need to wait longer simply after melting of the sample. And another point I want to show you is basically we have also in the grounds facility also other levitation, so electrostatic levitation method, which you can do similar kind of experiment. And in this case, this is just to remind you that you know from the transport coefficient, the dynamics of the melt is not changing a lot. So that's why you are expecting that also the viscosity are similar. And this is what we get actually with a comparison, the data from parabolic flight and also measuring the ones in our ground facility using electrostatic levitation. And you see that this is overestimated in a ground experiment. This is actually not a real viscosity, but it's due to artifact that we have the limit of possibility in the electrostatic levitation to overheat the sample. That's why, so we still have this, let's say, so the suspicion is we still have this layer of sulfur on the surface which affect the experiment. That's why the parabolic flight, experiment is much closer to what we are expecting. And just this brings me to the point that we will really need this kind of experiment if we want to study basically properly the viscosity or the melt property of these compositions, especially with the sulfur alloys. So this will be my summary of the first part. So basically just to show you a contrast of these two samples. So for the titanium base where sulfur content higher, we do see a change of the liquid dynamics. And for nickel-niobium sulfur alloys, we do not see much change on the melt dynamics of sulfur alloying. But it's likely due to the low sulfur concentration. This means that actually we are expecting a different mechanism why the glass forming ability is changed compared to titanium nickel sulfur alloys. And we have already done a first also solidification experiment with levitation. One can see that actually also the primary phase, which is forming from the undercooled liquid, is changing as a function of sulfur content. That's why we are starting to understand more than why this kind of system, which kind of roles sulfur is playing. The upcoming experiment on board the space station will be, we are very happy that can be also, I think this is a different proposal, but we are very happy that this can be involved also from our side on this binary alloy, because we are also interested in the binary alloy properties as a comparison. And the batch 4.3 will be then studying the sulfur containing alloys, both on viscosity and the other properties. Okay. So this would be my first part, and this would be a second part, which is slightly connected to the sulfur-containing alloy, but we are also look at different noble metal. So it's about actually a noble metal glass-forming alloys. One of them, which is famous, is so we have a slightly different team. So what we still have is also from Technical University of Berlin, and also one project partner from Denmark, Aarhus University. And so what the idea is to look at this basically noble metal-based metallic glass formers due to two reasons. So one is more physical reasons. So these are one of the best glass formers. So there are many, many data collected in this kind of compositions, especially for us, which is interesting, is look at this dynamic coefficient, when on the one hand viscosity, and on the other hand also the diffusion coefficient. And this is the only alloy where the diffusion coefficient has been measured over the entire temperature range where one have a liquid. So actually the melting point will be somewhere here, and usually we will not be able to measure this part because of crystallization, but because the glass forming ability is so good that we can access even in the cooled melt. What from our side a particular interest is here to look at the relation between viscosity and the transport coefficient, in this case diffusion. What is interesting is, especially in this region, what one can see is palladium is a major component, and it follows the trend of the viscosity, and the other small atoms, so phosphor, cobalt, and copper, they are faster in the undercooled melt. So basically one have a split of the transport coefficient, but one can say that basically the viscosity of the melt is driven by the large atom or by the majority component. They asked you some open questions, that's why we want to study that again. So if one look carefully, there's a question how transport coefficient can be transferred into viscosity, and there are different models, and we still see discrepancies. And this requires also more precise data in this region in a high temperature. I will speak a little bit later on why this is not so easy, because actually the alloy itself is not reactive, but there are a few reasons. The other motivation, in addition to the sulfur and phosphor, which I will show later, substitution is this is motivated by jewelry application, so one can really make some part of ring or similar component out of that, taking advantage of the good mechanical properties of the glass formers. So they are really resistant to scratch, for example. And in this case, there are a development of the palladium and platinum alloys, and what they find out in a structural point of view is there are subtle changes if one gradually substitute platinum with palladium, and for us and also the temperature depends. So if you look at the temperature dependence of the special shell, there are differences as a function of temperature, so expansion if you want. In this case, we are really interested in, sorry, it should be platinum, the ratio between palladium and platinum, and also other properties like heat capacity and crystallization behavior are changing with this ratio. Another aspect in this project is to really compare the sulfur and phosphor alloy. And this is again measured in the Tempus facility, so the parabolic flight facility. And we do have nice data. This is really a colorful image because due to the low melting point of the alloy. So the melting point is something around 500 degrees C or so. We have a new camera in the Tempus facility with an infrared spectrum and also high speed, and so would be also suitable to study solidification if the optical contrast is not good enough. So we measured at least one of the composition, which is also coming from the previous project. What is surprising is, if you remember that I told you in the previous alloy is that basically one of the transport coefficient is matched to viscosity. And this we do see large discrepancies. So in this sulfur alloy, so the diffusion coefficient is slightly faster compared to the phosphor alloy. But the viscosity, if you transfer that from the into diffusion coefficient, you see large differences. So this means that, yes, it's also for us a surprise that this means that either you have a much slower subsystem, so palladium, for example, or sulfur is connecting something strange. And we are currently studying the structure of this. The problem here is, so it's similar to the nickel niobium system, so we are limited in temperature range in a parabolic flight because it's not due to superheating of the surface layer, but basically at high temperature the sample is simply too low viscous that we can study it properly. That's why we need to always cool back to this temperature. So the first proof would be that if one have more temperatures in this region, to look at how the activation energy of the viscosity is changing in order to be sure that whether this is a different transport process. And since that, so it will be a batch 5 sample, so we are still have some time to go. But as I said, just to show you that we are interested here in 2 different aspects. So one is the difference between sulfur and phosphor alloys, and the other is the role between palladium and platinum. The other technical aspect is the problem why there are so few data in the high temperature viscosity is they are actually the alloy itself is not reactive, so they are actually no low melting point but have a high vapor pressure. That means that we cannot process that in the electrostatic levitation, which is in vacuum. To measure it classically in crucible had the problem that they have very bad wetting to many of the crucible materials. That's why you cannot measure viscosity in a conventional crucible experiment. Currently, we are exploring possibility to measure that in aerodynamic levitation, which we have also at the institute. But this is mostly designed for oxides currently, so we still need to benchmark this techniques with the experiment we hopefully get from the space station. And what we can do is already that with this kind of Levitator sample with aerodynamic elevation, we are studying the structure of the alloys or of the melt. And we are going to study also the solidification behavior of the melt, so phase selection and things like that. And with that, I'm done and hope that you are enjoying, you understand.
Yes, thank you. Thank you very much. Questions? I can imagine that sulfur and phosphorus are quite volatile. Is that correct?
Yes, that's one of, in the sense that, so preparation of the sample is a problem, but the Saarbrücken group, they have a much experience on this. Actually, it's not that volatile when it's alloyed in the sample. So once we make the alloy, it's okay. In the sense that if you process that in a inert gas atmosphere, for vacuum, it's a problem. That's why we cannot study this in the electrostatic, because it's in vacuum. But once you have some atmosphere in the chamber, it is okay.
All right, yeah, that would have been my next question. If you would not expect any compositional changes when doing successive melting solidifications.
So far, we haven't seen. So we have experience already in the Tempus facility. So far, we do not see much evaporation for one parabolic campaign. Yeah. That's why at least I expect that for some time one can process that. Right. Also on the space station.
Good, thanks. Questions, your opportunity. Yeah,
yes.
Damien.
I can speak loud.
It's for the online people.
Yeah.
All
right.
Hi, thank you. I'm not a metallic glass expert, so tell me if the question is silly, but from what I understand, you've been looking at materials that are relatively known glass formers, right? Would that be relevant, the use of the facility, the EML and all that, for materials that are, average glass formers? I'm thinking about those iron-based bulk metallic glasses that require quite a lot of cooling rate that can be that firm metallic glass, say for using melt spinning and lately additive manufacturing type of thing. Would that be these iron-based soft magnets, for instance?
Yes.
Would that be relevant, and is that something that you're considering?
Yes, there are actually already being iron-based glass forming composition done on a parabolic flight campaign. Yes, they are also looking at basically high temperature viscosities. So one of the key questions is, how this behaves. If you have high temperature data, how you can predict this part, then you can see whether this is acceptable, for example, for casting or for other manufacturing. But yes, this is of interest. Actually, they have been already additive manufacturing part on iron-based metallic glasses.
Very interesting, thank you.
Yeah, thanks, Damien, for the expert question, actually. Right, okay. If no more questions, we move on to the next presenter. Thanks again, Van.
Thank you.
So the next presenter is Florian Kagel from DLR, Materials Physics in Space Institute, who will be summarizing a couple of the EML projects as well.
Yeah, thank you very much, Wim, for the introduction. As you see, there's quite a number of projects that I'm quickly touching on in the presentation. I have to thank my colleagues, Jürgen Brillo, Thomas Volkmann, and Dirk Holland-Moritz for preparation of the slides. And I would say more people would have been here. And connecting to what Guillaume had said, sometimes seizing funding at a particular point in time makes collaboration and participation in conferences a little bit difficult. And it would have been better, let's say, for some respects, if the MAP program had continued. Perhaps more people would have been here. But nevertheless, I'm very happy to present recent findings in the electromagnetic levitation facility aboard the International Space Station in a number of projects described here. So I will introduce you quickly to the method. There is another EML presentation coming tomorrow where we'll go more into detail about the overall program, the different projects, the samples that have been so far processed, and a broader perspective, let's say, also in terms of output, science output. And then after that short introduction in the method, I will go and give you a short project status report on the different projects listed here. The last one, really a future prospect to what's coming next. So let's go into that. So the method is electromagnetic levitation. With electromagnetic levitation, you can measure two things. You can look into thermophysical properties. You have seen that in the previous presentation already to some extent. So we can look into specific heat, viscosity, electrical resistivity. And the second part is investigation of the solidification of undercooled melts with a focus on nucleation, with a focus on the growth dynamics, growth velocities, and delay times, and a couple of other things. And this is possible for various alloy melts as long as they are conductive. And of course, this can be done in the laboratory. And you see the picture here, how this is set up. So you have this coil system. You had seen the image, the live image that Fan Yang had shown in his presentation already before. Key point is, on ground, you need relatively strong electromagnetic forces in order to lift the sample against gravity. This leads to a deformation of the sample. At the same time, heating and levitation is coupled here. And you also have strong fluid flow inside of the sample on ground. So makes it difficult for some property measurements. Some measurements are impossible on ground. And for solidification, clearly there's an influence of the strong stirring. If you go to microgravity, then the coil system looks a little bit different. So it looks much more simple. But you have a superposition of two fields. You have a quadrupole field that basically holds the sample in position against the small rest acceleration that you might have. And then on the other hand, you have a heating field that goes in one direction that induces again eddy currents, and you heat up the sample inductively. And this also leads to stirring. And by, let's say, heating the sample up, and you have seen kind of this melting and cooling cycle. Then if you apply, let's say, this heating field to a certain extent during cooling, then you can also induce fluid flow in the sample at various levels. And this is also another opportunity that you have in microgravity to really vary the fluid flow conditions and then see what this has as an impact, for instance, on a solidification behavior. Of course, the microgravity experiments are one part only. Of course, this is backed up by a strong ground-based program using electromagnetic levitation facility, but also for some samples, electrostatic levitation. I think that I can skip more or less. So this is what Fan has shown you. So it's kind of this oscillating drop method to determine, on the one hand, the frequency of the surface oscillations, deriving surface tension from that, and the other one was the damping of this oscillation in order to measure viscosity. So let's go into the individual projects now. So the first one, I quickly showing some results, is the MagniFast projects. It's about nucleation and phase selection phenomena in undercooled melts with a particular look into the application to magnetic materials of industrial relevance. It's based on a ESA-HRE from 1999, so sometimes it can take quite a long time until you get things implemented. But nevertheless, refocusing, let's say, on science questions, there's still relevant parts that you can do. There's 4 partners from 2 different countries, so mainly US and Germany in this case. The idea is to develop a better understanding of microstructure formation in high-performance magnetic alloys, because this has also an impact on the material's properties, clearly. And there is various alloy systems of interest, hard magnetic materials like the neodymium iron boron, or the soft magnetic materials listed here. What we look into is measurement of growth velocities of stable and metastable phases as a function of undercooling, alloy composition, and melt convection. And the melt convection topic that I explained briefly before, ground-based strong fluid flow, ISS, EML facility, variation of the fluid flow conditions, and we can have a look on the impact of that. And it's clearly here providing experimental data for verification of theoretical models that describe, for instance, the growth process. So how does the experiment look like? So what is shown here is an image series taken of an undercooled iron 10 boron sample at an undercooling of 155 Kelvin. The time interval between frames is 0.8 milliseconds. And what you see here is the undercooled sample. It's still sort of bright. And then you see this bright spot here. And this is when nucleation starts. You get this bright spot. It's the latent heat that is released that leads to recalescence. And you can see basically this recalescence front propagation that aligns with the propagation of the growing crystal. And from that you can derive the growth velocity that is, yeah, I would say not very fast. I mean, you can have meters per second growth velocities in systems, and then you have systems that are a little bit slower here, like the iron boron system. So the point here is, for this relative moderate velocities in this space station experiment with low fluid flow, that you have in the system a small solubility of boron in the iron, which means during the growth of the iron, you have to enrich the solute ahead of the growing crystal, and you have to transport it away in order to get fresh iron towards the interface for the crystal to grow further. If you have no fluid flow in an EML experiment, like you have on the space station, then it's more or less diffusive. So you have diffusive transport of the iron to the interface, and you have diffusive transport of the boron away from the interface. And that restricts pretty much the growth velocities. If you do that on ground, you have strong stirring. This is the data up here. You have 2 orders of magnitude higher growth velocities at similar undercoolings. And this is simply because due to convection, I mean, you're transporting a lot of iron to the interface. And then you can see here nicely in between, when you vary fluid flow conditions, you end up with the growth velocity somewhere in between the ground-based data and data where you have low fluid flow in space. The second project is called Parsec, alloy rapid solidification with electromagnetic convection. What I will focus on here is the study of the transformation kinetics of metastable phases solidified in an undercooled melt with a particular focus on metastable BCC growth in iron alloys, such as iron cobalt, iron nickel, and a stable FCC phase that grows after the BCC phase, and in particular the transformation kinetics of that. So the key parameter here is the so-called delay time, and one can have a look on the delay time as a function of undercooling, alloy composition, and melt flow. And again here the interest is in the effect of fluid flow by experiments, comparing the 1G EML data with strong stirring and ISS EML data with a variation of stirring. So the experiment looks slightly different. So you see again, this is a undercooled iron nickel sample in this case, very deep undercooling, 230 Kelvin below the liquidus of the stable phase. And what you see here is the undercooled sample, so barely noticeable, quite dark actually. And then you see this bright spot up here. And the bright spot up here is related to the growth of the metastable phase. So for this deep undercooling, the metastable phase in this case forms first, the BCC phase, and then this continues to grow. So you see it's spreading over time, very high velocity here. So we have very short recording time, 45 kilohertz in the high-speed camera. And then at a certain point in time, you see another bright spot appearing here. And this is the growth of the stable phase that comes after the metastable. So you can have a look on the delay time as a function of undercooling. So there's this time lag between growth of the stable and the metastable and the stable phase. And you can plot this as a function of undercooling. And again, for different experiments with strong stirring, with slow stirring here and intermediate stirring, what you're able to do on the station effectively in microgravity conditions. And you see, well, that's the 1G EML ground data, strong stirring, and the delay time for a particular undercooling gets longer when you have no stirring. So clearly the fluid flow has an impact also on when the stable phase nucleates in the metastable phase and starts to grow. So this is work in progress. There's currently models that are developed to describe this delay time as a function of undercooling. There is a description already, I would say 2 models that are competing at the moment. And the second point is then to include this fluid flow topic as well. So focusing on going to another project now, CCMLCC, which is more into an application, which is in the area of electromagnetic levitation work, looking into chill cooling with a relation to continuous casting of steels. This is done by 4 partners from 3 different countries, headed by Charles-André Gandin from MinParisTech in Sophia Antipolis, who does a lot of modeling of the process and then space station experiments. The idea is to study the levitated steel alloys, how they cool and solidify when they get into contact with a chill plate. We will see that there is deformation happening due to solidification, shrinkage, and thermal contraction, and that induces fluid flow, and that has an impact on gross kinetics, microstructure, and the segregation profile at the metal-chill interface. It's gross kinetics during rapid solidification of the undercooled melt that one can look into, and you have, again, well-defined conditions under microgravity, so reduced fluid flow, no buoyancy, minimized electromagnetic steering, no external forces, spherical sample shape, so ideal conditions to start modeling this process and understand it better. And the space station experiments are really as a benchmark for verification and refinement of the solidification model that includes heat and mass exchange coupled with a thermomechanical deformation. And then one can apply this to continuous casting process of steel. How does the experiment look like? So you have the sample, you heat it up, you melt it here, you see the melting plateau, you overheat it, and then you start cooling, so you switch off the heater, you see that curve here, so heater switched off, sample starts to cool, and then at a certain point in time, still in the liquid state, you contact it with this chill plate that comes from top. So this can be moved up and down, so you contact it. Temperature is still measured when the chill plate is in contact with the sample through a borehole in the chill plate, a very tiny hole. And the sample itself is monitored with a video camera from the side. And we will have a look. So chill plate is contacting, sample starts to solidify, so you see the growth of the crystals here. It's deforming and yeah, fully solidifying. So and then, of course, this observation that one has in the experiment could be matched with the model that the colleagues from Sofia Antipolisas developed at MinParitech, and they described here in the model fluid flow induced and temperature evolution of the sample, shape deformation, and so on. So conclusions of this first part of the 3 projects. So we have seen distinct effect of the fluid flow and growth kinetics in the strong partitioning systems like iron boron. So growth velocity increases with rising fluid flow speed. We have seen that the delay time between the nucleation of metastable and stable phase is raised with increasing electromagnetic steering, and the chill cooling tests provide analysis of shape evolution due to the solidification shrinkage without the influence of gravitational forces, and this serves as a benchmark test for verification and improvement of these thermomechanical simulations. Let me come now to another project, which is called EcoProsol, which is on thermophysical property measurements and the solidification behavior of undercooled titanium, zirconium, nickel liquids that have an icosahedral short-range order. It's 3 different partners from 2 different countries. So Washington University, Kent Kelton, Worcester Polytechnic Institute, Bob Hires. The background to this is short-range order in the system and an idea to look into macroscopic properties of the melt, so density, viscosity, electrical resistivity, and specific heat, how this develops in the system when you start to undercool it. And we will see that there is really an impact. And there might be a relation between what the structure is doing in this system and how the macroscopic properties are reacting. And then one is also looking into crystal nucleation and growth in the system. So of course, there's again a question about the impact of fluid flow. So how is the solidification behavior changed? How are the properties of the solidified material behaving? And the system is titanium, zirconium, nickel primarily, but I will have another system that we compare against, and where we will see basically different behavior. So it's an icosahedral quasicrystalline solid phase that forms here. The system itself has an icosahedral short-range order in the liquid state as in the solid state for some alloy compositions. This icosahedral phase is chemically highly ordered, so it asks for diffusion limited growth, and you have sluggish crystal growth velocities that are comparable with the fluid flow velocities. So what the scientific objectives are is a better understanding of structure-property relations in undercooled metallic melts, the study of the influence of structure in the solid and liquid on the solidification behavior, and an investigation of the impact on fluid flow and nucleation and growth processes in undercooled melts. So that's a quick glimpse into theory. You don't have to go through that into detail, but let's say what I would like you to take away is, so you have classical nucleation theory. You can calculate the nucleation rate in this form, and there's this pre-exponential factor, and this depends on interfacial attachment kinetics and the diffusion in the liquid. However, in the systems that we are looking into now, it's not that simple, because this means that you shouldn't have a difference between, let's say, the growing nucleus and the liquid. However, in the systems that we are looking into, there's a difference between composition of the growing solid nucleus and the liquid, which means you have a pileup of the solute, and that, of course, impacts on the nucleation rate. And there's a coupled flux model by Kelton to describe this, and this works pretty well, as we can see in the data later on. So, and this predicts a reduction of this pre-exponential factor for systems that show this behavior. On the other hand, if you have fluid flow in the system, then during solidification, this is predicted to enhance the transport, similar to what we have seen with the iron boron system, where we were transporting, let's say, the iron with fluid flow towards the growing interface. And in the same way, this could work for the nucleation. Then the other point is probability of nucleation in a temperature interval. There's the model by Skripov. And so this can be used, let's say, to fit nucleation statistics that you acquire from the EML experiment. So how does this work? You do quite a number of experiments, actually quite many. And you plot, let's say, this undercooling statistics, simply how many times did you solidify the material at a particular undercooling. And then you can describe this curve, let's say, with this model. And from that, you can derive two important parameters, this A star parameter here and the sigma parameter. And you can compare that. So this has been done for two systems. So the vitralloy 106, shown here, and the titanium, zirconium, nickel. So what do we see here on the right-hand side? So this is the experimental analysis. The analysis of the experiments using the model, basically. And so what we get is, let's say, an average undercooling from fitting this nucleation statistics. And this is on the one hand for vitralloy 106 and for the titanium, zirconium, nickel down here. We get then also parameters for shear rate and fluid flow velocity. So basically using different types of stirring on the sample in the experiment. And we get the pre-exponential factor here. And what you see is clearly a difference between the two systems. So for the vitralloy 106, we see there's an order of magnitude change in the pre-exponential factor with varying the fluid flow in the system. And also this has an impact on the average undercooling that we get from the nucleation. So which clearly shows stirring in this case has an impact on the nucleation. For the titanium, zirconium, nickel alloy, which is a congruent melting alloy, so where basically the solid has the same composition as the liquid, you have almost no impact of the on the pre-exponential factor within, let's say, the error bar that you have here. And even when you vary, let's say, the shear rate and also the average undercooling remains the same, more or less. So a second point of interest for these liquids is thermophysical properties, particularly here the viscosity measurement of the titanium, zirconium, nickel alloy with two different compositions. This has been done on the ISS for nickel 21, nickel 10, and for the nickel 21 also in electrostatic levitation on ground. Data is shown here in an Arrhenius plot. So you have logarithmic scale for the viscosity. You have an inverse temperature here. If it's Arrhenius behavior, it should be a straight line. So you clearly see a deviation here if you go to lower temperatures. And in particular for the nickel 21, it was possible to really deeply undercool the sample here. And this deviation from Arrhenius behavior at lower temperatures can be understood with this power law fit, basically, which is predicted by mode coupling theory. So this is a glass forming system, should behave or should show this power law dependence. Exceptional really is here that you can very, very deeply undercool the system. And if you look on the viscosity's absolute values, it's not changing an awful lot. So you have 800 degrees and it's only an order of magnitude change in viscosity. Still relatively low in viscosity. The link now to the structure, and so there must be an origin perhaps also in the structure, is the measurement of the electrical resistivity. So please focus on the red curve here. So this is electrical resistivity as a function of sample temperature. So again, here's the liquidus, we undercool the sample. And what you see here is that this resistivity is rising here. It's more or less constant initially, and then it rises. And resistivity is relatively sensitive to structural changes on a shorter scale. And so this indicates, could be indication that there is, let's say, some ordering going on in the system at these low temperatures. If you look here, 1400 degrees in this area, it's roughly where this lift of viscosity happens. So this seems to align somehow. So let me come to the final two projects. One from an early ESA-HRE in 1999 named CoolCop, merged then into the project Li-phase, so liquid phase separation in metallic alloys. Yeah, you see this strange partner and country denomination. Well, due to retirements and so on, there's currently a restructuring going on in this project. So we are going from 7 to 4 partners and from 5 to 3 different countries. We have industry involved here as well. And so the scientific object is to better understand, let's say, solidification in liquid alloys again, but also at the heart of that was looking into demixing alloys, this cobalt-copper system shown here. So fluid flow is dominating the buoyancy on Earth, and by interfacial fluid flow is dominated by buoyancy on Earth and by interfacial forces in space. And so what this system does, the cobalt-copper system, it has it shows demixing in a metastable state. So you undercool below the liquidus, so it's this black line here, and then you hit on a binodal and you start to demix this system into 2 liquids in the undercooled state. So eventually you might start to form this kind of compound droplet, so consisting of liquid 1 and liquid 2. And then you can, if the system is still not crystallizing, if it's in the undercooled state, you are able to measure interfacial tension according to a method proposed by EHRE. So effectively, instead of getting the Rayleigh frequency, let's say here, you have a split and you have 2 additional frequencies in omega plus and omega minus. The omega plus is pretty prominent, the omega minus is difficult to detect. But from that, so if you have this compound droplet, you should be able to get interfacial tension. The colleagues from Japan are working in the ELF facility on slag iron systems with an application, let's say, in the steel industry to better understand slag iron interaction. Here you could do that in this, let's say, demixing undercooled metallic system, but it requires a fully separated sample. So experiments have been carried out on the space station on cobalt-copper, not quite as expected because the sample undercooled initially quite well during the first cycle, but then had difficulties to undercool later on. We will see shortly perhaps why. But from this first measurement, let's say this data was obtained, so you see the Fourier transform here, so you see the intensity for different frequencies. So this is exactly looking into the oscillation as a function of temperature. And you see, well, this Rayleigh peak is changing in the undercooled liquid state. So this is the green data here is undercooled liquid. And you seem to develop an additional peak here, and this main Rayleigh peak seems to disappear. Of course, you can ask the question, so where's the relevant omega minus peak? So the black data here is a calculation from a simple model, assuming that you have droplet in droplet effectively. And, well, you end up with these data points here, and then you have to search where the relevant peak is. You might ask if this perhaps might be the relevant peak, but if you then do a calculation, well, you get interfacial tension values that are pretty much off what you would expect. So the question is, what is the problem here with this sample? So one idea was perhaps oxygen contamination, but that can be ruled out from the post-mortem analysis of the sample, so there was no oxygen inside. However, what was found was a lot of other stuff. And this is stuff that came from the other samples, basically evaporated and then somehow stuck on the cobalt-copper, and that might also explain why there were difficulties with undercooling. Analysis is currently still ongoing, so it's not so easy to understand and describe this. So to conclude now, I would come to the project Oxytherm. This is something new, really, that will be on the space station with the relevant facility to measure oxygen content soon. And this is looking into the change or the behavior of thermophysical properties, surface tension, viscosity for liquid alloys under oxygen influence. A lot of partners, a lot of countries involved. Associated partners, collaborators from the US also for batch 5 experiments. And so what is the scientific object? So liquid metals are, of course, very reactive, as we know. And even in a levitation experiment where we don't have contact with the container wall, at least, and don't get contamination from that. We might still pick up some contamination from the surrounding atmosphere. So we might pick up oxygen from the surrounding atmosphere, and we might get, therefore, some changes on the properties. And this can be quite significant, as you see down here. So what is shown here is a function of temperature, surface tension for different alloys. And you see here basically iron, pure iron, behaves as expected. Surface tension goes up with decreasing temperature. If you add a bit of oxygen, the surface tension goes down significantly. And on the other hand, also the behavior changes. So at high temperatures, you might still have this increase with decreasing temperature, but then you start to decrease here. From a practical point of view, this can have impact on what is happening, let's say, in applications like welding. So gas with some impurities, so you have oxygen, Marangoni flow is reverted, you get this very deep and shallow wells. If you use clean gas, it's getting more broadly, fluid flow is changing in this case. So it's interesting really to measure this. So far, there's only ground-based experiments. As I said, the possibility on the space station is upcoming. So this is from liquid titanium. Surface tension as a function of oxygen content and at a particular temperature here. Experimental data taken in the laboratory in an electromagnetic levitation facility. And you see the experimental data points here. Relatively constant initially, up to about 1 atomic percent oxygen, which is quite a lot. But the reason is that titanium gathers the oxygen, takes up a lot into its volume. And at a certain point of, basically when a certain content is exceeded, then the oxygen, of course, starts to accumulate at the surface, and then it has an impact on the surface tension. Can be described well by associated Butler monoatomic model here. So, and the ideal description here is clearly deviating. Yeah. What is interesting also is to know how much oxygen is really on the surface. You wouldn't obviously get that from the experiments that are done in the EML, but it would be interesting, let's say, to have a hand on that as well. So the ideal model again fails here, and if you look on the other models, I mean, they pretty much describe the point where you have the solubility limit well. So we are looking forward to that. So there's an oxygen control sensor to be implemented for the facility up on the station, and then surface-sensitive properties can be measured, bulk-sensitive properties can be measured. So let me give a short outlook. So this lists upcoming experiments for the delay time we have in batch 4 and batch 5, some further samples for the gross velocity, another iron boron sample in batch 5, chill cooling, upcoming batch 4, batch 5 again, icosahedral ordering, again in batch 5, completing part of the batch 3 experiments. You might have seen the blue data has been restricted in temperature, and this is to be extended. So there was a problem with sample processing, and another batch 5 looking into icosahedral phase. For the phase separation, there would be 2 samples cobalt silicon upcoming. This is together with other colleagues and related projects, Elfstone and USTIP. And in the OCS, there's a number of things coming up also again with collaboration with NASA colleagues and related projects. So it's really collecting data on various systems, alloy concentrations needed for verification of theoretical models. And we are very thankful for ESA for the support of not everything listed here, but all the project I have just described and the flight opportunities. DLR Space Administration in Bonn, that was quite a lot involved in getting the EML facility to the space station. It's a joint project, basically, between the national agency and ESA. And we like to thank the German, European, and international project partners. We like to thank the national funding agencies that fund the work. And we should also mention and acknowledge our colleagues at the Institute, but also from MUSC that do the operational support. And a couple of names, non-exclusive, are listed here, without whom it would not be possible. And I see a representative from MUSC at the back, Jean-Paul Diavera. Okay, thank you very much for your attention. Looking forward to your questions.
Thanks. That was a lot of information. Any questions? Yep.
Hi, I'm Peter Hartmann from Hungary. So my question was a very naive question. I've done anything like this. So when your main parameter was always the undercooling temperature, delta T, how sure can you be that the temperature that you measure from the outside is actually the same as in the inside, especially when you have crystal growth and the latent heat is transferred? So how?
Yeah, so of course you have a small temperature gradient from the outside to the inside, that I would say, because you're cooling the sample from the outside. I think there's calculations, it might be of the order of 5, 10, maximum 20 Kelvin perhaps in these liquids. Not that much. And of course, I mean, you have seen in the undercooling experiment, when you have crystal growth, that where the recalescence happens, basically the sample is, depending on how deep the undercooling was, heated up to the liquidus temperature, and the remaining part of the liquid still is in the undercooling temperature that you had initially. Mm-hmm. Of course, depending where you look with the pyrometer, I mean, there's a fluctuation in temperature clearly. Yeah.
Mm-hmm. Okay, thanks.
Thank you. More questions? Seemingly not, which is okay. It will mean that we'll finish this session a bit earlier than expected, which will kind of extend our lunch opportunity. We will reconvene at 2 in the afternoon in this particular room for a session on what we call the facility definition teams. And those are teams of scientists that have been thinking with us on post-ISS research needs and capabilities. So that would be an interesting session, I would say. All right, so well, hope to see you all back at 2.